circuit theory, saying that what we have done, introduction to electric circuits, and what we will be doing in circuit analysis course. You know, this is the circuit analysis, the continuation of introduction to electric circuits. So in that explanation, we said we're going to use two different domains for circuit analysis in circuit analysis course. One of them was the frequency domain. Now we will be examining the frequency domain. The first thing we need to know is why we do need that frequency domain. We've got to explain that. And what is the basics in this domain. So it's going to be two parts. One of them is the why the frequency domain. So this is going to be a bit long video, because in here we need to know the reason why we need a new domain, because there is another domain as well. So all these requirements coming from practice. That's why we've got to know why do we need that. That's why it is a bit long video. This one is going to be a long one, and then we are going to use another video for this chapter, circuit theory in frequency domain. What we are going to do in frequency domain is explained here, but why is explained here. So we're going to start with this one. Let's go inside. It says here frequency domain. Inside the frequency domain, we said, in frequency domain we are going to use sinusoidal functions as sinusoidal function as sources or inputs. So we've got to know what this sinusoidal signal is. Sinusoidal signal is in general is a fundamental signal of electronics. So that is an important function or a physical quantity that we need to know. So these signals could be the basic energy source and information signals. So the sinusoidal signal is not only the energy source or input, energy source as an input as an energy source. Also, it is an input for an information carrying source. That's why it is doubled importance it includes. So what is this signal? Let's go in. This signal mathematically is this function. So you have seen that function. This function has got three parameters in it. One of them that Vm, the other one is that omega, and that is called angular frequency, and that phi is the angle of this function. So three parameters. So first of all, this function is the function of t. So that t is independent variable. Vt is the dependent variable, which is function. And this function has got three parameters in it. So let's examine these parameters step by step. That Vm, since the cosine max and minimum values for a cosine function is plus minus 1. So we know the limits of cosine function. So Vm is the coefficient of this. So that means Vm, the maximum value. If this cosine value is plus 1, so it's going to be plus Vm, the highest positive value. And when it is minus, so the highest minimal value. So this coefficient is called amplitude. In Turkish we call it kelnik. And that is the signal's Vm value. Highest maximum value. That m comes from the maximum value. This omega is the coefficient of t. It's called radial frequency or angular frequency, and it's equal to 2pf. That f is the frequency of that sinusoidal function. There is another term that we use for this frequency, which is the inverse of it. Inverse of frequency is called period. So let's explain that what these frequency and periods are. So when you look at that signal, we could see that this signal, that part of this signal, is repeated. So that t time interval, the shape of our function, is repeated for every t period time. That's why we call it, this is a periodic signal. So that means the shape, the same shape, is repeated consequently. So this time interval here, that repeated part of our function, is called, this time interval is called period. So this period, inverse of this period, is called frequency. What does this mean? Inverse of it, how many of those t's are included in 1 second? 1 over t means in 1 second how many of these t we have got. This is called a special term for this. It is called frequency. That means how many of those signals we are going to see in 1 second. So it is called frequency. So if you know the period, you can find the frequency. If you know the frequency, you can find the period. So that is the second parameter. The third parameter is related, which this is called phase. In Turkish we call it faz. Is related that phi. How we can determine this? If you make the cosine, this part is equal to 0, that gives you the maximum value. That means that maximum value. When this is equal to 0, isn't it? So when you make this equal to 0, phi is going to be is minus omega t. So from that t, if you make it equal to 0, that t is going to be this. So that tells me where this signal's maximum value starts. If the phi is equal to 0, so my sinusoidal function is going to be this one. Cosine function is going to be this one. If there is a phi, then it's going to be the one which is shifted to the left side. What amount? That amount shifted to the left hand side. So that phi determines how much you're going to shift it. So that phase change is shifting, or the angle of this cosine function changes, means this signal is shifting. If this is positive, shift left. If it is negative, shift right. So it is the opposite of what is we expected. So when it is positive, it goes to left side, so it goes that way. If it is negative, it goes that way. So that means these are the three parameters that we are dealing with. Now if we come to, so in practice, normally if there is a cosine function, physical cosine function that we are dealing with, then we wonder what these parameters are. So you're going to measure these parameters. But one of the parameters, the most critical one, is that angle, or amplitude. That amplitude. Why is that? Because in practice, this is the signal that we could observe in mains at home. That means the basic power source at home. So we know that the frequency of this signal is 50 Hertz. This 50 Hertz comes from the production location, isn't it? Where you produce that signal. So there is a generator, that generator's round time tells you that frequency. So that frequency is known and this value is 50 Hertz. in Europe and in America as well. In America it is 60 hertz, but in Europe it is 50 hertz. The frequency is hertz. Meanwhile, I have forgotten to tell that. The phase, we know that the phase depends on when we are going to turn the switch on off, because you could get this signal at any time. This any time determined by that angle. So angle is related to what time you're going to turn on and turn off. So that phi measurement is not that much critical. What is left is that Vm. So in general, if there is a signal, normally to measure the value of that signal, if it is changing with time, not easy to observe with an analog meter, because when it is changes with time, if it is changing a bit faster, you can't follow it by your eye. So what we normally do, get the average of that signal. That average is the area underneath the function. So in order to find that for this sinusoidal function, it is critical because the average of this signal gives you 0. In this time, what we do, take the square of this function. When you take the square of it, that minus becomes plus, and this plus becomes the square of it, so the function becomes positive function. So that means that is this. So if you take the average of this and transfer it to this y coordinate divided by t, so that is the area. When you divide it with t, you get the average value here. But that average is the average of the squared function. Find the average of the original function, you've got to get the square root of it. So of all these operations gives me a value. That value is called RMS value. RMS comes from the root of the mean value of the squared function. Mean value of the squared function, RMS. So the avometer or voltmeter measures that RMS value. So if you measure the voltage of the mains at your house, you're going to measure that RMS value. That is 220 in Europe. So if you do the calculation, you end up with that RMS is equal Vm over square root of 2. Then if you multiply your 220 by 1.41, you get the Rm value. So that is important in order to find out this Vm amplitude. So that is sinusoidal function. So give some examples here. Mains at home, wall socket. Amplitude is 200, so this is not 2 but 0, 220 times 1 over 41, that's the square root of 2. RMS value 220 volts. T period is 20 milliseconds, frequency is 50 Hz, this is Europe case, and phase depends on the switching time. That is the most common sinusoidal function that we face, which is our energy source, electrical energy source. Another example is given here. For example, maximum value 1.5 volts, frequency 1 Hz, period is 1 second, and the angle is 45 degrees. Is here. That is the time interval between two peak values is the period, 1 second here. And that is Rm value. This is 1.5 volts that you could see it here. So 45 degrees, that means you shifted this cosine function to the right. So it is minus 45, it should have been. So let's see now the second step. So what we have seen mathematically, what this sinusoidal function is, what are the physical signals in this form, sinusoidal function, a sinusoidal signal. we gave these examples. So let's remember now what we have done in Introduction to Electric Circuit. We find the first and second order circuit analysis. Dependent source was DC source. In this course, we examined DC source driven circuits, first order as second order. In order to solve these circuits or analyze the circuit, we solve the differential equations since they have got L and C elements in it. And the solutions of these differential equation includes homogeneous solution, particular solution, natural solution, forced solution, general solution are found. So that is one of the such circuit solution here. Mathematical ones and the physical ones. Physical ones, natural force type of solutions, and the mathematical ones, homogeneous, and the particular solutions. So why we got three lines separated here? That is, if the characteristic roots are real and complex or multiple roots, what are the solutions here? So let's examine in general. The first part here shows the homogeneous solution, that is exponentially decreasing function. When the complex roots, this is once again exponentially decreasing function in the form of sinusoidal function, and this is the multiple roots case. Once again, this function is also decreasing function, exponentially decreasing function. So what does this mean? Physical in exponentially decreasing function means this function's effects could be limited in time, because when you increase the time, this value is going to disappear. So that means after a few seconds in practice, this is going to disappear. That's why we call this homogeneous solution at the same time transient solution, because it is going to disappear. What is going to left? This is the general solution. So this part is going to disappear. So we are going to observe this part. This part is the particular solution. So since it is the long time observed solution, we call this solution at the same time steady solution. In Turkish we call it sürekli hal çözümü. So that means we are going to observe the particular solution after a few seconds. So it is this form is also similar in the physical case. When it is natural and the force solutions, we are going to observe the same thing. So some part is going to be transient solution part, and the other part is going to be steady part. Now this tells us something. If we are not dealing with the first a few seconds what's happening in the circuit, then only the particular solution or the steady solution is enough for you, for we, to observe. Because most of the time we are going to observe this solution, not this solution. This solution is going to disappear. So conclusion, shall we calculate particular solution only, not this part? Because we are not going to deal with this part. There might be some special cases that this part is important. One of them is the stability. If this circuit is astable, this is going to be exponentially not decreasing but increasing. In this case, that means your circuit is going to burn. That means your circuit is astable, not stable. So it could be important. That's one importance. The other important, in some cases, we've got to know this transient part as well in practice. I'm going to give you an example for this. But in general, and especially in electronics, the particular solution is enough for us to know. So we might prefer to calculate particular solution only. That is the solution. That is the conclusion that we can get out of this frame. Now we said in the introduction to electric circuit we have used these sources as DC source, but from now on we will be using the sinusoidal sources. When you see the sinusoidal sources, this is a simple circuit, RL circuit, and there is an independent voltage source here, and this is a sinusoidal voltage source here. At the solution of this, we're going to write the state equations for this. That's the state equation for this circuit. For this from this state equation is the differential equation, linear differential equation. It is just one because one state variable we've got. This is inductor current, that is IL, which is this IT. So this loop current is also the current of this L element. So this current here is the inductor current as well. So if we're going to solve this differential equation, is going to have two parts. One of them is homogeneous part. The second part is the particular solution. How we can find this particular solution step by step will be explained in another video, so you could follow that, or you could follow it in the course as well. So when you look at this homogeneous part here, so this is exponentially decreasing functions, as we said already. These exponentially decreasing functions seen whether it is the independent source, DC source or AC source. Still that homogeneous solution is a decreasing function. And this decreasing function, that means transient solution, that's going to disappear. If you look at the particular solution here, we could get out of this some conclusions. One of them is this. You know, this is a differential equations, so the solution is the inductor current. Inductor current is going to be the particular solution. Particular solution is going to be in the form of the source. Source is sinusoidal, so that our particular solution is going to be sinusoidal function as well. So if you are looking for find out a sinusoidal function, you've got to find the three parameters of this function, because we know the form of this. So this is the given independent source. If you're going to find a particular solution of these elements, current and voltages, it's going to be cosine function, but the parameters will be changing. The one of the parameter, which is frequency, is not going to change, because when you take the derivative of this, it's going to be sinusoidal function again. Derivative of a sinusoidal function is another sinusoidal function of which frequency does not change. Therefore, these elements, current and voltages, sinusoidal functions, frequency is going to be the same as this independent voltage source frequency. So I do not need to calculate this frequency because I know that it is equal to the source frequency. What is left is the amplitude and the angle. So you see here, that is the particular solution. This particular solution, that is also at the same time steady solution. This part is the common as the source. What is left, this coefficient here, which is the amplitude of our solution, and this angle is the angle of our solution, affects the angle of our solution. That phi is the source phi. So from that we could see here these two parameters will be calculated. The frequency, no need to calculate. So this amplitude of my solution depends on the source amplitude, that Vm, depends on the R and L values. These are the circuit elements parameters, and also, that is the critical part, depends on the source frequency. Similarly, if you look at this angle here, that's theta, you're going to see that omega L over R. So this angle also depends on that frequency. So that means the solution, the particular solution that we are dealing with, which is a sinusoidal function, all the parameters depends on the frequency. That means frequency domain, name comes from it. Everything depends on frequency, that's why it is called frequency domain. So let's go into the details of this frequency domain. So here, maybe it is need to explain here. This is a second order circuit in general for different type of roots, what we're going to observe. You see here, sinusoidal function, that is the particular solution, that is the transient part of it. So this is going to disappear, we are going to see this part only afterwards. Here, that is the transient part. After that, you're going to observe this part only. Here you are, that's transient solution, you're going to observe this one. So for different type of roots, transient solution disappears after a few seconds, and then we're going to observe only the particular solution. That's why calculation of particular solution might be enough for us to calculate. So let's come to new domain business now. New domain, limitation, advantages, disadvantages. Let's compare the time domain and frequency domain. In time domain, you could use any source. In frequency domain, the independent sources should be sinusoidal sources only. You cannot use different type of sources. Or if you've got a different type of sources like DC or exponential or pulse functions, then you cannot use that frequency domain. You need the S domain maybe, that we're going to explain it. So in time domain, for any sources, we can calculate all the solutions, that means homogeneous particular natural force. In frequency domain, we will be considering only the particular solution, and we have seen that transient solution is going to disappear. Steady solution is going to be the particular solution, so that's why we only find the particular solution in frequency domain. No transforms need in time domain, but there is a transformation from time to frequency domain in the frequency domain. That's an extra job that we should do. And the method, system, state equation, state differential equations. So we are going to see that in here, this differential equations are not used anymore, will be linear equations. The only difference, LC elements included linear equations we are talking about. That's why these linear equations will have the complex coefficient matrix. So we're going to see it. But this is linear equations, not differential equations in terms of the within the context of the comparison. So in here we've got differential equations, we've got here linear equations. State variables, inductor currents and node voltages. In here, the variables that we're going to find are going to be voltage and current phasors. So this is a new term that we're going to examine later on. No inverse transform required in time domain, and there is an inverse transform in here. So at the beginning, from time to frequency domain. At the end, from frequency domain, go back to the time domain. There is a transformation. These transformations are simple transformations that we're going to see. Again, in time domain, we could observe the stability. We can make the decision about whether the circuit is stable or not. But in frequency domain, we cannot say so. So this homogeneous part of the solution determines the stability. Now we compare those two domains now, and we said we are going to prefer the particular solution and not dealing with the homogeneous solution, but in some cases the homogeneous solution or the transient solution might be important. That is an example for it. This is asynchronous electric motor representation in circuit. So if you look at the values, you could see it. These are the wires, resistance which is very small. In the motor you've got wiring, wired rounded wires, and then L 1 Henry, it is a quite high value because it is a motor, part of the wired wounded wire. So that is the electric representation of the asynchronous motor. The solution is going to be this one, and if you replace the t with that is half of the period, 10 milliseconds, in that time you're going to see a value 2 amp. That current is 2 amp current. A high current value drops immediately after 30 seconds. 30 seconds is going to be 1 amp, so it drops immediately. So what does this mean is this: if you want to protect the motor from the high current value, you're going to put a fuse here. Let's say your motor properly works half amp. Then if you put here 1 amp fuse, that is going to burn if the current is more than 1 amp. But at the beginning we have seen that we might see a high value current here. For this current, this fuse is going to burn. That means your motor is not going to run because of that current, the transient solution current. So that's a problem here. How we could solve that problem? If you introduce delayed fuses, 2 or 3 amp delayed fuse, then what happens is this: so this fuse is not going to work when you see this current at the beginning because it is delayed. And then when this transient solution has passed, so it works properly, means when there is a problem in the motor, that fuse is going to burn, not due to this inrush current. That's why sometimes the transient solution might be important. That was an example for you. But this transient solutions becomes important in most of the time in electrical engineering, not electronic engineering. In electronic engineering, that transient solution is not that much critical in general. Conclusion is this: in these cases, particular solution calculation only might be useful. That means frequency domain analysis will be useful. Then comes the reason for that. That means why steady particular solution? For a stable circuit, after a short time, transient solutions disappear and only steady solution will be observed. That steady solution is the particular solution. So if in this new domain, if we calculate this, that means it's going to be a new domain. In this domain, there is a basic concept which is called phasor. So let's examine what the phasor is in this domain. Since particular solution is to be found in omega domain, this solution will be in the form of dependent source function, that is sinusoidal, with the same frequency, angular frequency. Sinusoidal functions can be represented as phasors. Let's see what phasor is. So that's Euler formula, we know it in mathematics. So if you got a sinusoidal function like that, you can represent this function in this form. Real part of this function. Look at this function, Vm over e to the power g phi multiplied e to the power j omega t. So if you open with this one, if you use that formula in here to this, you're going to end up Vm cosine omega t plus phi plus j Vm sin omega t plus phi. So if we take the real part of it, you're going to end up with this circuit. So what we have done here, we are saying we can represent this function by using the Euler formula in this form. If we look at this inside here, in here we've got omega term, exponential term, and there's another complex number here, which we see the amplitude and the phase only of this signal. So this coefficient is called the phasor of this sinusoidal function. That means once you see the sinusoidal function, you can easily say that the phasor of this function is Vm times e to the power j that angle. So we can easily figure that out. That's the phasor of this signal. So if you know the function, you can easily say the phasor. If you know the phasor of a function, you can easily say that corresponding function in time domain to this phasor. All you've got to do, you know that these are going to be the elements current and voltages. If you know these element currents voltages phasor, then you can find these elements current and voltages in time domain. All you've got to do, multiply it to e to the power j omega t and take the real part of it. Or in short, when you've got this phasor of this signal, then you're going to write the cos omega t as part of the independent source, because we know independent source frequency is going to be the same for the elements current and voltages sinusoidal function. So this part is the same, only parameters that we are dealing with is the amplitude and the angle. So this amplitude and angle is included in that phasor, so you can write this amplitude and phasor here. Once you know the phasor, you can write, you wrote this already from the source, and you're going to write that Vm is the amplitude of your complex number here, also the amplitude of your sinusoidal function, the angle also the same as your phasor angle. Similarly, we could consider a sinusoidal function, not cosine but sine, and then you're going to take the imaginary part of it rather than real part of it. So if our source is cosine form, so you're going to take at the end real part. If it is sine form, you're going to take the imaginary part of it. So conclusion, phasor is phasor of a sinusoidal function. If you've got a sinusoidal function, phasor of it is a complex number. This is a complex number. Includes phase and amplitude. Includes phase and amplitude. Do not include frequency. That phasor do not include the frequency. Transformation is easy. So if you know the function, you can easily find the phasor. If you know the phasor, you can easily find the function. So we said we are going to deal with sinusoidal function in this course. So this is alternative representation of sinusoidal functions by using phasors. We just explained that. So let's go in now. Since it is a complex number, bir ara verdim, bunu sonradan sileceğim. Since this is a complex number, it could be in the Cartesian form or polar form. So we should, from time to time, we might need to transfer the Cartesian complex number to polar form, or the polar form complex number to Cartesian form complex number. How we could do it easy, so you can represent in coordinate system here, one point, that's the real part of it, the x-axis, and the y-axis, the imaginary part. So you can represent this point. If you know the A and B, that means abscissa and ordinate is known, then you can find that point. Or in polar coordinate, if you know this theta angle and that D value, that means polar representation. You can get the same point. So you can represent any complex number in Cartesian form with A and B, or in polar form with D and theta. So how we're going to change from one to another is easy. If you know the A and B, you can find that theta and D. If you know the A and B, then D is equal to A squared plus B squared, square root of it, this one. And what is theta is arctangent B over A. So tangent theta is B over A, so theta is arctangent B over A. The other way around, if you know this D and A, how you're going to calculate A and B, is easy. A is equal d times cos theta, B is equal d times sin theta. So the one thing that you got to remember when you are trying to find that theta might be critical, when this A and B's, both of them minus, both of them plus, one of them plus, the other one is minus. In this case, how are you going to make the decision about the angle value is easy. You've got to check which quadrant your complex Cartesian number is in. If it is first quadrant, in general, we could say that without taking into account the sign of these A and B values, use the amplitude values and calculate this theta. How are we going to determine the sign? I will explain it to you right now. Saying that once you found the theta, if the original Cartesian complex number is first quadrant, so you can directly find theta. That's going to be a plus value. If your complex number is in the fourth quadrant, so whatever you've got to find, you have found arctangent B over A, you're going to put minus in front of it because it's going to be in this area. First quadrant means A is plus, B is negative, isn't it? So it's going to be whatever theta you found, you've got to find minus theta here. If it is second quadrant, so your point is, or complex number is here, but you have found the theta here, all you've got to do, P minus theta gives you this. So if you know the arctangent B over A, when you consider B and A without any sign, and then find the theta, P minus theta gives you the second quadrant complex number polar representation angle. If it is third quadrant, you're going to add plus P here. So plus P theta gives you this third quadrant complex number polar coordinate angle. So you've got to do some practice. There are many examples in the book, so you could do that your own. So we finished here now. What we explained here is this. If you find a particular solution only, that is going to be simple for us, and that's going to be enough for us to do our analysis. And then, since the sources must be sinusoidal, so sinusoidal function represented by the phasors, we end up with a conclusion like that. So that's going to be useful for us. The second video is going to explain to you how we're going to see the circuit theory in frequency domain. So that video has finished now.